Hello, my name is Jean-Baptiste Bouvier. I'm a postdoc at Berkeley, and today I'll present the work I've done with Kartik Nagpal and Professor Nick Armer. It's called Police-RL, Learning Closed-Loop Robot Control Policies with Provable Satisfaction of Hard Constraints. To guarantee safety in RL, we need hard constraints that cannot be violated. And that's typically done with control barrier functions or reachability analysis or projection onto some safe set. But all these methods require white box dynamics, which are typically not available in RL. On the other hand, safe RL has used control barrier transformers or PPO barrier to train a neural network to approximate a barrier function. The problem is the safety depends on how well this neural network approximates the CBF, and so the guarantees are lost. Our goal is to guarantee safety in closed-loop constraint RL. So here's our framework. We have a black box system of state S and action A, and affine constraint CS less than D, and we try to learn a deterministic policy in this closed loop to optimize the reward over theta while satisfying the constraint at all times after training. Our insight is that given a non-safe area inside the state space, we will design a buffer in front of that area so that trajectories need to go through that buffer in order to reach the unsafe area, and we'll try to make this impossible. To do that, we first estimate how nonlinear are the dynamics inside the buffer B through sampling. Then we use the police algorithm from Yann LeCun to make the policy affine in B. Everywhere else in the state space, we let the RL algorithm optimize the policy to maximize the reward. And then, because their policy is affine, we only need to check at the vertices of the buffer. So that's just a discrete number of checks to verify whether the policy is repulsive and prevents trajectories to cross the buffer anywhere and hence guarantees safety. So that leads to our theorem where we define our buffer B, and if the policy is affine, and we have an affine measure epsilon of how nonlinear is dynamics in the buffer, our repulsion condition only needs to be checked at the vertices V of the buffer and guarantees constraint satisfaction at all times. We implemented our algorithm on a simple 2D system that learns to reach a target while not crossing constraints, red here. And this is just TD3. Regular learning algorithm gets a penalty every time it crosses a constraint. You can see the arrow gets red when it crosses a constraint, and it actually never learns to reach the target without crossing the constraint. On the other hand, our policed RL algorithm ensures the policy is affine in the buffer B so that the arrows you can see are all kind of together and they always point away from the target and learns much faster. We also implemented this on the KUKA 7-degree robotic arm, tasked with reaching a green target while avoiding a red constraint area. Using reward shaping with TD3, it just takes a penalty every time and reaches a constraint, violates a constraint. Using a soft constraint approach like CPO with a violation threshold set at 0, gets too timid and never gets close to the target. Whereas our policed approach is pushed away by the buffer in blue here and reaches the target green. And so when you look at the numbers, the TD3 is pretty bad at verifying the constraint, whereas CPO is good. You get 90% of constraint satisfaction, but almost never reaches the target. And we only have 90, not 100%. We don't have safety guarantees. There's the same issue with PPO barrier. We do not have safety guarantees that our policed algorithm provide with 100% constraint satisfaction. And still very good completion task, so we reach the target almost every time. And so takeaways are that our police RL provably enforces an affine constraint, only needs a black box model of the environment by learning an affine policy, and safety verification only needs to be done at a discrete number of vertices, and so that's tractable. Thank you for attending.